Okay, I'm going to start right now, so your friend might join later. So we're going to talk about the third part of the SVM today. Just as a recap, we talked about the bounding and cross-validation error previous lecture, and we mentioned that we only care about those support vectors when you find your margin and the distance between your classifier, which is P or rho here. So that's a red line. What we're going to do is, through the QP optimization programming, so quadratic programming, we can find those support vectors shown in blue here, like x1, x2, and x3. And these are the parameters that show us what the actual value of P is, and if those change, we should also change the line L, and definitely the P will change as well. And these 4 points, x7, x8, x7, x6, 4, and 5, since are not support vector, they're not going to affect the way we classify this problem here. So if you remove them as well, nothing will happen here in the middle, because this fat margin only works with the support vectors, right? So that was just a recap of what we mentioned last session. So we say x1, x2, and x3 are the support vectors. And the cross-validation error works with the summation of all point-wise error divided by n. And you see that all the time, since the classification is done right, if you remove those 4 vectors, we don't change much about the classifier itself. Right, and also we talked about how we're going to deal with the cross-validation error. We mentioned 2 cases. The first case was, we suppose xn and yn we chose is not a support vector. So those 4 points here, x4, x5, x7, and x6. And we talked about that since the classification is done without any error, so d minus n, which was the data set containing all the points excluding that point which was not a support vector, en would be 0 as well, right? And we mentioned also the second case, so I'm just recapping it quickly. And we suppose xn and yn was a support vector, right? So by removing that, we're going to have a pointwise error, which is an identity function of the classification error. So that was the output for the d minus n, which is not equal to the real value, right? And we mentioned that the bound for the ECV, so that's the bound, is not related to the number of samples itself, but just the number of support vectors, right? So this is a very good and promising property about the SVMs, that the complexity of the model is not increasing by the number of samples, but just by the number of support vectors, right? You're going to use this in many examples if you want to compute the cross-validation error bound using number of support vectors, right? And we pretty much stopped here in the previous lecture. So today we're going to talk about other ways to view SVM problems. So say another perspective. All right. So today we're going to talk about Lagrangian dual formulation. So we mentioned that now that we know the bound is related to the number of support vectors, how are we going to identify those support vectors, right? And it's going to be done through the Lagrangian dual formulation. So in optimization theory, I'm just going to provide a very short brief on what a Lagrangian duality is. So in optimization theory, duality is just looking at the problem from another perspective, right? So you have a primer problem. So that's your first problem, let's call it G, we call it primal. Then you can, if it's a convex problem, you can change it to G prime, which we call it the dual problem. In a convex world, so normally these two have the same optimal solution, right? So sometimes when we cannot solve directly the primal, we can transform the problem into a dual form, and then we solve that. And the optimal solution for that would be the solution for the primal. So this is what the Lagrangian duality is. So given a nonlinear programming problem known as a primal, there exists another nonlinear programming problem closely related to it, right? And it receives the name of the Lagrangian problem. So under certain convexity of assumption, we gotta find that the primal and the dual problems, so these two problems, have equal optimal objective values. So suppose your first primal problem was your SVM that we talked about in the previous two lectures, right? You wanted to minimize WTW given conditions that yn WX1, W2X2 plus B was greater or equal than 1, right? So that was our primal problem. So by applying this Lagrangian duality, so it's a function, you can transform this into a dual form. And I'll show it in the next slide. And we know that under the assumption of convexity, both problems will have the same optimal objective values, right? So this is an important property we can use here for SVMs. So another example. So suppose this is your primal problem, right? You want to minimize a function, the function fx, right, for the values of x. So given x, you want to minimize fx, and it is subject to this constraint, which says gi of x is smaller or equal to 0, right? So that's your constraint. So the duality of this problem can be defined as this, and it's unconstrained. That's why we call it infinity here. So in this case, when the primal is minimization, the dual is always the other way around. It's maximization. So the maximization of fx plus the summation of ui gi's. So these parameters are coming from the Lagrangian function, right? I'm going to show you in the next slide how we're going to transform the first problem of the SVM, or the primal problem, to its dual form, right? And we're going to use the same notion in order to find the support vectors in SVMs. So now if you want to find the optimal values for this, how you're going to do that? You're going to use the gradients of fx, right, and equal that to 0. So given the parameters you had, in our case we want to find the w's, right? So we have to solve the problem given w, and we're going to find the optimal solution for that, right? And the optimal solution for this is likely to have the same value as the optimal solution for your primal problem. Okay, so let's go back to the SVM and see how we're going to use the Lagrangian duality in SVMs. So that was our primal problem. We wanted to minimize 1 over 2 W transpose W, right? Such that Yn multiply W transpose Xn plus B was greater or equal than 1, right? So that was our primal problem. Right? So now, if we use the Lagrangian duality, so we're going to define a function of L Lagrangian, which has 3 parameters, W, B, and alpha. So now we want to find these parameters, right? And in the duality form has, just like what I mentioned in the previous slide, the primal form, which was the fx on the previous case, which is here, minus the summation of all the n's from 1 to n, alpha n, which is a parameter we introduced using in the Lagrangian form, and we want to find it, right? We call it dual variables, the alphas. Yn multiply W transpose Xn plus Yn B minus 1. So this is a dual Lagrangian. Now we have several alphas to find as dual variables, right? So this is a dual form of the SVM. Now let's see how we're going to find these parameters. All right. So now we need to maximize. So previously we were minimizing with respect to, so this is called with So previously we were minimizing with respect to W and B, and we wanted to find these parameters as the optimal solution, right? So if we found this, that would be the optimal solution. So because using these two, we could find L, which was the line for the SVMs. Now in a duality form, this is the dual case, we maximize with respect to alphas, right? So, just like what I mentioned 2 slides ago, when we want to find the parameters, in this case, we want to find against W. So we need to get the gradients of Lagrangian function and equal it to 0 and treat W as a parameter, right? So the previous formulation becomes W because it was right, that was that. So the gradient becomes W, and the rest is the summation of all the n's from 1 up to n, alpha n, Yn, Xn, right? So now we need to solve this. So in this case, W would be, you bring the rest on the other side. W would be the summation of n's, alpha n, multiply Yn, Xn, right? So now using the the gradient of the dual, we can find W this way. Okay, so now that we find W, we can find B as well, right? So in order to find B, we need to get the derivatives of the Lagrangian function with respect to B, and it would be equal to minus summation of alpha n's yn, right? So now B is gone here because that was a parameter, and it's becoming 1 on the first derivative, right? So now we can calculate W and B this way. All right, so we had this previously, right? We had this long form of Lagrangian, 1/2 double transpose W minus this. Now, if you factor in W transpose here, you're going to have 1/2 W transpose W minus W transpose. And we just figured this in a previous slide, which was W, right? When we found the gradient of that. So this amounts for W. Right. So now if you want to find alpha for that, so the form corresponding to alpha would be the summation of all the n's from 1 up to n alpha n minus 1/2 double summation of over m and n's. So now we need to find these parameters. So there are a bunch of alphas here that we define in a dual form. And in the generalization form, we want to maximize this value subject to alphas, right? And at the same time, we want to have the summation of alpha n's yn equal to 0. So now we're going to see how we're going to find these parameters. So in the general form, you see that the dual problem is also a quadratic programming here, which is sort of obvious because the primal one was also a quadratic programming. It has a quadratic form in the objective function and a linear form in the constraints, right? So I brought up the formula here again on top. So you have this value as your Lagrangian form given alphas. So now we define, instead of this long form of alpha m's, alpha n's, we define this way. So we define a matrix of M which is a long form of y1, y1, x1, t, x1 up to xn, xn, xn transpose xn, right? So instead of writing it this long form, we're writing as 1 over 2 alpha transpose M, which is this huge matrix of alpha, pt alpha, right? So this is another way to showcase in the vector format. So your p's also would be defined like this, minus 1s. And the bounds would be, as we discussed, alphas are from 0 up to infinity for all the i's from 1 to n. And that's going to be the final constraint. W transpose alpha is equal to 0. You don't have to memorize this, just to let you know that this form can translate into the vector format. Because anyways, in order to solve this, you need a solver, and in the exam, you won't be asked for such a question. All right, so now let's see what we're going to find from this, right? So that was the Lagrangian form. L of alpha was equal to 1 over 2 alpha transpose M alpha plus P transpose alpha, right? We define both matrices, P and M. So now, given its duality property, if alpha star, which is the solution for this, right? If alpha star is a solution to this dual problem, using that alpha star we found from solving this, you can find W's now, the vector of W. And the vector of W would be the optimal solution for the primal problem now. Okay, so there is this last KKT condition that I'm going to just showcase here before I stop, and is when you want to solve this, you end up with this formula, alpha n multiply this value, and the result is equal to 0, right? So alpha n multiplied by yn w transpose xn plus b minus 1 is equal to 0. So using KKT condition, it's intuitive to assume when this value is 0, either the first one is 0, which is alpha, or in the case that this wasn't 0, the second portion of the formula would be 0, right? So now we have two cases. Either alpha n is 0, or if alpha n wasn't 0, then this must be 0, yn w transpose xn plus b minus 1, because at the end of the day the outcome was 0, right? So either of these two must have been 0. So now using so this is called KKT condition. It's a general property we can find from the first order derivatives, and in this case it's going to be helpful for us, because if we analyze these two cases, we're going to figure it out if those points were support vectors or not. Okay, so now finally using these two that are either alpha is 0, alpha n is 0, or the rest could have been 0, we can come into the conclusion in two cases. The first one is alpha n was 0, right? Then it's obvious that it does not affect w, right? And when it does not affect w, thus we can understand that the xn, that point that we picked using this, can be removed from the dataset D, because it was not a support vector, right? And the solution will not change. So that was the first case. Now the second case, if alpha n wasn't 0, so the second portion of that formula was 0, yn multiply wx plus b minus 1. So we understand that the x is going to affect w, right? Thus xn and yn is a point on the margin, right? So say that was the line, and that was the margins. So in this case, it's going to be this point on the case of 2. On the case of 1, it could have been this point. case 2, case 1. So this is a support vector because changing this will affect the classification boundary, right? So this is the outcome we can find from solving the dual problem and finding the alphas. Okay, so I'm just going to stop here and conclude with the final session on Wednesday. What remains from SVM is the nonlinear transformation and kernel tricks, and that would be all. Okay. Any questions? Okay. So see you on Wednesday.